Hi, Grace. Thank you for joining EPAM Ukraine. Devoxx
Hi,
Ukraine.
thank you so much for inviting me here.
Nice to see you. What topic have you prepared for us today?
So we're going to be taking a deep dive into sort of reactive systems and event-driven architecture and where they fit together.
Sounds great. Okay, it's your time to shine. The mic is yours.
Great. Thank you so much. So thanks again for inviting me here to Devoxx Ukraine. It is my first time presenting sort of, I guess, virtually, but in the Ukraine. So lovely to meet sort of a new developer audience. And as I've said before, we're going to be taking a deep dive into sort of reactive architecture, reactive systems, and event-driven architecture. So my name is Grace Jansen. I'm a developer advocate at IBM in the UK. And if you want to reach out to me during this talk, after this talk, my Twitter handle is up on the right-hand side there. So it's at GraceJansen27. Feel free to follow me, tweet me, whatever you want to do on Twitter. So without further ado, let's get started. So as every great demo seems to start with, we're going to start with a coffee demo because everyone seems to like coffee, although ironically I don't. But anyway, coffee demo time. So let's take a look at a coffee demo where we've got some coffee lovers sort of representing microservices, and they're going to pass in coffee orders to a coffee shop microservice via HTTP. Then that coffee shop is going to pass those orders to a barista microservice to make those coffees, so to process those orders, again via HTTP. This is kind of a classic example of using a fairly synchronous, fairly blocking form of communication, and sort of was what we used to do back when we first started sort of creating applications like this. And if you only have a couple of coffee lovers, this might be absolutely fine. But what happens when you start getting lots and lots and lots of requests, lots of coffee orders coming through your system, and you've got a large amount of data that you're having to pass through everywhere and get processed? So if you want to take a look at this example, it is on GitHub. It was made by our cousins over at Red Hat, and you can check it out at the link at the top of this slide. But essentially, how do we take this sort of more traditional form of architecture and improve it for large amounts of data, large amounts of requests, and sort of our really event-driven world that we're currently in? Well, that's where we introduce event-driven architecture. So event-driven architecture, if you haven't come across it, it's a really popular architectural approach that enables events to be placed really right at the heart of our system. So we've got a basic diagram here. Events here, what we're referring to is really a state change in the system. And so what happens is those events are stored on this event-driven messaging backbone. So you can see here we've got microservices that are publishing to that backbone, and we've got microservices that are consuming from that backbone. And some of those microservices here in this diagram, once they've consumed, are also doing some sort of processing and then publishing their own events to that backbone. So it really places events at the heart of the system and enables us to sort of loosely couple these microservices with their exchange of information. So let's see what happens when we introduce sort of this event-driven architecture form into our example. And actually, this second example, the second version of the same application, is also available in that GitHub repo if you want to take a look at the comparison between the two. So now that we've introduced this event-driven, this event backbone into our application, you can see here that we're still passing orders into the coffee shop via HTTP, but now once those coffee orders are in the coffee shop, they get added to an event backbone. So they get added to that topic or that queue. And then once they're in that event backbone, the barista can then pull or consume from that backbone whenever they're ready to create the next coffee order. And once they've created that coffee order, they can then update the board. So in the original example, our coffee lovers were having to sort of, if you can imagine, wait at the till for each of their coffee orders to be processed. So it's a fairly blocking process because the coffee lovers had to wait to get a response from the barista and had to wait to get their coffee. And they could only order really one at a time. Whereas now our coffee lovers can place their orders, and instead of having to wait at the till for each of their coffees to be produced, they can go and sit down, have a chat, talk about Java, as we all love to do, and then they can wait until the board's updated to tell them to go and collect their coffee. So it's a much more asynchronous process. So you can see here how we're trying to add in some of that asynchronicity and non-blocking behavior, and how event-driven architecture can help us to do that. And often when we're introducing event backbones, one of the most commonly and most popular tools that we can implement is Apache Kafka. So if you've not come across Apache Kafka before, it's an open source distributed streaming platform. And it's sort of different from traditional messaging systems in that it has this stream history. So it has this immutable data that you can go back and read again if you want to or if you need to. It enables scalable consumption. It's very scalable in itself, and it really enables that high availability of information that we're looking for when we're building systems. So now that we've added in this event-driven backbone to our Barista example, it often leads to questions like this. So is my coffee shop now non-blocking and highly responsive? In other words, is my microservice system non-blocking and highly responsive? And people often assume the answer is yes, because we're now using this fabulous tool called Kafka. Unfortunately, that's not the whole story. What we actually need to be considering is every aspect of our application and how the different components of our application interact together to make sure the entire application from end to end, or the entire microservice system, is non-blocking and highly responsive. And this is where reactive systems comes into play. So reactive systems, what do I mean by that? What does that term really sort of signify? So the reactive systems is sort of an overarching concept for describing systems that sort of follow these behaviors and characteristics that are laid out in the Reactive Manifesto. So here's the Reactive Manifesto, and it's based off 4 key characteristics, or cornerstones they're often referred to. So the underlying characteristic that we need to see when we're trying to build really responsive, really reactive, non-blocking applications is this message-driven sort of asynchronous backbone within it. Now, interestingly here, it's message-driven and not event-driven. So I mentioned event-driven architecture, and often when it comes to Kafka, there can be various assumptions that Kafka is designed for event-driven architecture only. Interestingly enough, in the original Reactive Manifesto, so Reactive Manifesto 1.0, they were using the term event-driven, but they switched to message-driven in Reactive Manifesto 2.0, which was produced in 2014. And if you want to learn more about why they made this switch, there's an entire blog article you can check out online where they do describe why they made this transition. Let's take a look at what the difference really is, though. So on the left-hand side here, we've sort of come up with a definition of what a message is. So a message is an item of data sent to a specific location. And on the right-hand side, we have a definition for events. So an event is a signal emitted by a component upon reaching a given state. So really, it's that differentiation between sort of just emitting that signal and letting subscribers subscribe to it if they want to know, versus sending it to that specific location. So that's the main difference between those two. But if you think about it, interestingly, you can actually have a message that can contain an encoded event in its payload. So you can have this sort of weird mesh of both. But really, what matters is when it comes to Kafka, it doesn't matter whether you're doing message-driven or event-driven. When you look at the Apache Kafka website, they don't mention events or messages at all. In fact, they refer to records. So you can see here on the right-hand side, they refer to publishing and subscribing streams of records, storing records in a durable way, or processing streams of records as they occur. So actually, with Apache Kafka, you can design a system that's either message-driven or event-driven, or maybe even a mix of both. So Apache Kafka is a fantastic tool that we can utilize to introduce this asynchronous message-driven backbone that really allows us to decouple the components of our application and achieve some of those other reactive behaviors defined in the Reactive Manifesto. So let's take a look at our original Barista example, and let's look at why you can't just add an event backbone in or a tool like Apache Kafka and expect it to be highly sort of non-blocking and responsive and reactive all the way through. So we're going to take a look at a couple of problems that we might come across and why the other behaviors that are defined in the manifesto really matter when we're designing reactive systems. So in our example, we only had 3 coffee lovers at first, but there are not only 3 coffee lovers in the world. There are many, many more. So what happens when we suddenly have an influx of coffee lovers trying to place coffee orders at our coffee shop? Well, more coffee lovers obviously means more coffee orders. So we've now got our event backbone, and that means that we can add these orders to the queue. So although our coffee lovers aren't having to necessarily wait at the till for this synchronous process, they're able to sit down and asynchronously wait for their coffee to be served, we still have a blocking component in our application. And that's that barista microservice. So we only have one barista trying to process and produce these coffee orders. So that barista can only work so fast. So we're going to be restricted by the speed at which that barista can produce these coffee orders. So we're going to have a fairly slow coffee order process because that barista can only work so fast, and our coffee lovers aren't going to get the best experience they possibly could because we've got that blocking and that sort of bottleneck within our system. So instead, what we need to be implementing is this elastic behavior. So really enabling our system and the resources within our system to both scale up and scale down depending on the fluctuating load to our system. So elasticity and building in elastic behavior into our application can help us to gracefully deal with these load changes over time and also keep our application as cost effective as possible by not only scaling up, but also scaling down when necessary. So let's take a look at our Barista application again. So in this case, if we were able to scale up the number of Barista microservices or perhaps the replicas of that particular microservice, we'd be able to get through those coffee orders much quicker because now we've got more baristas processing those orders. So in this regard, by elastically scaling our application, due to that fluctuating load, that increased load of more coffee lovers and more coffee orders, we're able to provide a much more responsive, reactive, non-blocking system. So that's why elasticity is really important. Let's take a look at another potential problem we could come across. So we've got an additional component to our application, and that additional component in this case is a serving table. So essentially this serving table is where the barista has to place the coffees before the coffee lovers can come and collect them. Now this serving table is essentially representative of a downstream component. And that downstream component could be an additional microservice that needs to do some additional processing. It could be a third-party application. It could be a third-party database. So it's representative of something downstream that we need to be passing those orders to, all that data, all those messages to. So what happens in the potential failure point of, okay, our coffee lovers are being a little bit lazy today. They're not coming to collect their coffee as soon as they should be. So now our coffee orders are building up on this table to the point where our barista is now trying to juggle coffee because they can't put it down on the serving table. So now our serving table's blocked, our barista's blocked, and we can't produce any more coffee orders. So this is a potential blocking point and a potential point of contention in our system that could potentially cause failure and an unresponsive system or an unresponsive coffee shop. So this is where we need to introduce resiliency. So resiliency is all about building in resilient behaviors into our application so that we can gracefully handle any potential failure to our system. As software developers, as hard as we might try, it is virtually impossible for us to predict every potential failure we might come across with our system. So it's really important that we build in natural resiliency within our application in the face of those potential failures. So with the Barista example, we could potentially have provided some sort of feedback mechanism from those downstream components, maybe the barista or the serving table, to the upstream components to let them know to limit the rate of requests coming through, or to maybe spin up some more replica microservices or replica serving tables or replica baristas to help us deal with that potential bottleneck or potential point of failure. So resiliency is a really important behavior when it comes to creating really non-blocking reactive applications. Because if parts of your application goes down, you're naturally not going to have a reactive or responsive application. So we need to be resilient. Now, these three characteristics all lead to the last characteristic of the Reactive Manifesto, and that's responsiveness. And when we say responsiveness, what we're meaning is to be as responsive as possible to events or to state changes within our system. So really being responsive to those sort of changes, be it maybe a input or data from a sensor, be it a click on a website, any form of state change, we need to be as responsive as possible. And by implementing these four behaviors, we can really achieve non-blocking reactive behavior end-to-end throughout our application and throughout our system. So I've mentioned these sort of very high-level behaviors that we need to be implementing and thinking about. But how do we actually go about building these in and building reactive systems? So here you have sort of a fairly basic application. It's only 3 microservices big, but it's just to demonstrate the various levels and layers that we need to be thinking about. So we already mentioned Kafka and how providing sort of this event-driven or message-driven backbone can be particularly helpful in terms of enabling us to have decoupling and really reactive behaviors at the data level. But our applications aren't just made of data. They're made of microservices, they're made of various different components. So we also need to consider the behavior between those components and within those components. So when it comes to the interaction and the behavior between those components, we need to make sure that our components are interacting together in a non-blocking and reactive manner. And to do that, we can introduce these concepts called reactive architecture patterns. Now, I've got some examples here of sort of what constitutes a reactive architecture design pattern, and these are some of the 4 most commonly used patterns that we've come across. There are many, many more if you wanted to take a look. We haven't gone through them all today. This isn't an exhaustive list because we'd be here all day. So if you wanted to take a look at some additional design patterns, feel free to just Google the phrase reactive architecture design patterns, and you should get lots and lots of resources that will help you sort of learn about the various other patterns you can utilize. But let's take a look at these 4. So we've got CQRS. So CQRS stands for Command Query Responsibility Segregation. And that's really all about separating out that read and that write API to enable really high availability of that data. Then we got circuit breaker. So if you've ever done sort of electrical engineering, it's a very similar concept. So with circuit breaking in software, what we're referring to here is if a downstream component is maybe stuck in a process, maybe it's gone down or it's under extreme stress or load, it can essentially the upstream components can recognize those maybe like a repeated failure message or a repeated log message. And essentially that upstream component can temporarily put a stop on the requests or the messages or the records going down to that downstream component. And it can reroute those requests to an alternative, maybe a replica microservice. And by doing that, we enable this downstream component to not become a contention point and not become a bottleneck. Instead, we give it the time it needs to recover, to come back online, maybe to get through that process it's stuck in so that it becomes healthy again, and we can reinstantiate that route for requests to that downstream component. Then we have sagas. So Saga is sort of a mechanism to take more traditional transactions that we normally would have done in maybe a more monolithic architecture and do it in a more distributed manner. So we create these sort of multiple microtransactions that have this fallback behavior to account for things potentially going wrong partway through. So it's essentially a sequence of local transactions where each of those transaction updates data within a single service. And then we have backpressure. So backpressure is another feedback mechanism, this time from the downstream component to the upstream component. And it's essentially what I was describing that we could have utilized in that Barista example. Backpressure is where the downstream component is able to feed back to the upstream component to help rate limit so that that downstream component doesn't become overloaded or overstressed and become a potential point of failure or a bottleneck or a point of contention. So these are some of the patterns you can utilize in your application, and we'll actually be coming back to backpressure specifically in some of our examples later when we look at some of the reactive frameworks we can utilize. So we've talked about sort of the interaction between our components, but what about within our components? Within our components, we also need to make sure that the programming logic is also non-blocking and highly responsive and reactive. And to do that, we can utilize reactive programming patterns. So we looked at reactive architecture patterns. Now let's take a look at reactive programming patterns. But what do I mean by reactive programming? Here's a brief definition of what reactive programming sort of is. It's essentially all about focusing on this asynchronous style of programming. So it's all about driving forward the logic forward via the availability of new information instead of by this thread of execution. So really drilling in that concept of asynchronicity into the programming within our microservices. And we can implement this by introducing various different patterns, and some of these are included here. So we have things like future. So I imagine many of you are familiar with this as it's in the Java language. So we have futures, which is a promise to hold the result of some operation until that operation completes. You can also utilize reactive programming libraries. They're really designed for composing asynchronous and event-based programs, and they're actually utilized by many of the reactive frameworks and toolkits that we'll go into later in this presentation. But essentially, some examples include RxJava and Small Mutiny. And RxJava is a really popular language. If you're not using Java, or if you're interested in other languages, you're also able to get this Rx sort of library in various different other languages like Go, Scala, Node, etc. Then we have the reactive stream specification. Now, this is really a community-driven specification that's designed as a standard to help you handle asynchronous data streams whilst also providing that all-important backpressure. And again, this specification is often utilized by many of the reactive frameworks that we're going to be taking a look at. So these are some really useful patterns to use when you're implementing asynchronicity and reactive behaviors into the programming logic within your microservices. So we've looked at how, we can look at the various layers and the various levels of reactive systems and introduce reactive behavior. But how do we go about really utilizing Kafka to build these reactive systems that are really event-driven? So we'll go through each of the behaviors in the Reactive Manifesto and examine how we can implement sort of various configuration options to really make sure that our applications are displaying as many of these behaviors with best practices as possible. So the first of those behaviors was message-driven. And as we've already discussed, Kafka really enables us to implement this message-driven backbone and this decoupling between components. So let's take a look at, and we'll go straight into resiliency. So in terms of resiliency, Kafka, just by nature, has built-in resiliency in it. So the fact that Kafka has this stream history and this immutable data within that stream history means that if a component goes down, it can come back up and reread those various records or messages in that stream history. So it makes it extremely resilient in the face of microservices going down, for example, or needing to reread a particular record for various reasons. And this is different to traditional message queuing systems, because in traditional message queuing systems, once a consumer has read from a particular topic, that record is then removed from that topic queue. So it doesn't have this sort of immutable data built in to the actual sort of backbone of messages. So it's a really useful tool that we can utilize and feature that we can utilize within Kafka applications to really enable that resilient behavior. Kafka also has this resiliency built in with the way that it sort of sets up its clusters. So when you set up a cluster, you essentially have various different brokers. And a cluster usually has a minimum of at least 3 brokers, and we'll see sort of why we need at least 3 later on. But within these brokers, we break it down into topics. So topics are essentially where we store our records. And what we're referring to here with a topic is essentially a logical grouping of a similar kind of message or record. And it's up to you to define which messages or records go into which topics. So, for example, with our coffee example, our coffee application, we might have one topic for maybe coffee orders, and we might have one topic for user information updates as an example of different topics and different groupings. Within a topic, we then have one or more partitions, and these partitions are distributed across Kafka brokers. We'll see sort of why partitions come into their own with elasticity in a minute. But in terms of resiliency, the key thing that we need to be thinking about here, the key feature that Kafka offers us that really enables resiliency is the use of leaders and followers. So for each topic in your Kafka cluster, one of the brokers is elected as the leader and the other brokers are elected as followers. So essentially what happens is all of the apps connect into the leader broker and they consume from and produce to that leader. Then replication works across the followers as the followers repeatedly fetch messages from the leader, and this is all done automatically by Kafka. So in this example here, we've asked for 3 replicas when I set up my Kafka cluster. So we have 1 leader and 2 followers, as you can see here. So broker 1 is our leader, broker 2 and 3 are our followers. But what happens in the potential case of the leader going down? So if the leader goes down, well, the great thing is that we still have 2 copies of our data in our various followers. So that's already some resiliency built in because we haven't lost all our data. The other sort of resilient characteristic that Kafka offers us is this leader election. So if one broker goes down, so in this example, broker 1's gone down, so we've lost our leader. What happens is Kafka initiates this new leader election. So a new leader is elected from the followers that are still healthy, and our apps are automatically told to transfer across to this new leader broker. So this is fantastic because essentially we don't lose any data and we're able to reinstantiate the system and allow that broker to come back online eventually and rejoin as a follower. So we have backup of the data in the various followers because we have replicas of that data, and we have this automatic leader election. So we have some great resiliency behaviors really built into Kafka itself. But what about our applications and how they interact with Kafka? How do we make sure that the records from our app are actually successfully being sent and consumed from Kafka? So let's take a look at how we introduce resiliency into our producers, first of all. So if you haven't come across the term producer before, a producer is essentially the name of an application that's sending records or messages to Kafka. So a couple of things that we need to be considering when we're trying to introduce resiliency into our producers is delivery guarantee and the configuration that we need to enable to get those delivery guarantees. So with reactive and sort of resilient systems, we can't just do this fire and forget method if we want proper resiliency. Because if we do fire and forget and our broker goes down and we've only got maybe none of the brokers got the message when our brokers went down, or maybe only one got it and they've gone. Essentially, we can't guarantee that those messages have been stored successfully or have been received by Kafka successfully. So instead, we need to be considering these two guarantees. So either at most once or at least once. With at most once, you may lose some messages. It's not completely resilient. So if you don't mind some of the messages making it, then at most once might be something you'd like to consider. But if you need guaranteed delivery, so complete resilience, then it's at least once that you want to be considering. But you do need to remember that you may get some duplicates if you choose this delivery guarantee method. So you just need to be considering that in your application logic. And we can achieve these delivery guarantees by configuring two different configuration values, and that's ACKs and retries. So ACKs stands for acknowledgement, and that's essentially an acknowledgement that's sent when the records or the messages have been received. And we can set that ACKs value to various different things. So if we set ACKs to 0, that's essentially for when we don't really care about the message being acknowledged. It's really good for fast throughput, but not good for resiliency. We can also set ACKs to 1, and setting ACKs to 1 allows us to make sure that the leader, at least, successfully received the message. So we'll only get that acknowledgement back when the leader acknowledges that essentially they received the message. So we know at least one broker got the message. But if we want to be sort of that at least once guarantee and we want to be completely resilient, we can use ACKs equals all. So if we set ACKs to all, that essentially it makes it wait for all of the replicas to confirm they successfully received the message or record. So by using all, it does slow down the throughput, but it does enable us to have guaranteed delivery and a really high resiliency within our application and within our producers. Then we also need to be considering retries. So what happens if our ACKs times out or perhaps fails? How often do we want to retry, and how many times do we retry producing the event? The thing we need to be considering here when you're thinking about retries is that you need to consider how that retry might potentially affect the ordering of your messages or your records within Kafka. So that's just something to consider. But by enabling retries and by setting that ACKs value correctly, we can really enable our producers to be as resilient as possible. So we've talked about producers. What about consumers? So producers send messages to Kafka, consumers consume messages from Kafka. So when we're consuming these records from Kafka, we need to make sure that we know which messages we've read and processed and which we haven't. So for this, we need to be thinking about offsets. So an offset is essentially the value associated to a particular record on a topic, and it essentially just adds 1 every time a record is added to that topic. So we start at 0 and it goes up and up and up and up, as you can see in this diagram. In other messaging systems, the reason we need this offset and the reason we need to be considering this within consumers is because of this stream history that we have within Kafka. So in other messaging systems, we don't have this issue because once the record or message has been read by a consumer, it's no longer on the queue, but this isn't the case for Kafka. So this means we need to keep track of where the consumers have gotten to reading the stream of records or messages. So this is why we need to be considering offsets. You need to store your offsets somewhere. Usually it's stored in a topic on Kafka, and we call an API to commit that offset. But there's 2 different ways that we can commit that offset, and there's 2 different ways of us keeping track of where that consumer's gotten to. So that's automatic and manual. So we're going to take a look at the Barista example here again to really see the difference between setting at that offset commit to either auto commit or to manual commit. So here we have our Barista. Our Barista is our consumer in this case, and we have a topic. And in our topic, we have 3 records or 3 orders for our coffee lovers. So let's take a look at how committing offsets and how this affects the flow of our application. So if we have auto commit, this means we have no code in our application to sort of state when we want to commit that offset, but instead we're relying on the default settings in the underlying client, probably a Java client in this case. So this client will essentially commit that offset on a timer basis for the messages that we've read from Kafka. So with the barista example, our barista, our consumer, starts reading from the topic. So we take that first order and we start processing it. So we've got that coffee order being processed. So because we're on an automatic commit here, we're on a timer basis because we're relying on the underlying client for this and the default settings. So our barista's been making the coffee for some time. So automatically, due to the timer basis, we get this coffee order. We've committed this offset for this coffee order. However, unfortunately, our barista is a little clumsy and drops the coffee. This is representative of that consumer maybe going down midway through processing. So when that consumer comes back up, when the barista eventually clears up and gets back to making the coffees, when they go back to reading the topic, they'll see that they've already committed the offset for the coffee. So instead of making the coffee, they move straight on to the cappuccino. So instead of making 3 coffee orders, we now only have 2 coffee orders when we get to the end of our topic, or the end of the records or messages in our topic. So we don't have very good resilience here because we've lost one of those records. We've lost that coffee order. So instead, what we can enable is manual commit. So manual commit really means that we're introducing code within our application to state when we want to be committing that offset. So in this case, we're not going to commit the offset until we've served the coffee. So we finished processing the coffee and we've served the coffee to our customer. So in this case, our barista starts making the coffee, and you can see that tick doesn't appear until we serve the coffee to the customer. And the same can be said for cappuccino and latte. So in this regard, even if the barista had dropped the coffee midway through making it, we wouldn't have committed that offset. And so when our barista comes back online and looks at that topic again, it can see that it needs to start right from the beginning at the coffee order again. So this is a great way of introducing increased resiliency by committing these offsets manually and determining exactly when you want them to be committed in your consumers. Kafka also enables us sort of extra resiliency because it really enables this decoupling that we've mentioned earlier. So it enables us to decouple the components of our system. So if one microservice goes down, it doesn't bring every other microservice down in the system because we're sort of decoupling it by having Kafka in the middle. And we can sort of utilize Kafka as a communication mechanism. And essentially, we can, when writing a set of microservices that communicate with Kafka, we have to consider sort of the shape of the records being sent and received. So if a producer changes the shape of records being produced, this change could break consumers, and it might imply that there's still coupling. So although it does introduce this decoupling aspect, and it is helpful, we still need to consider the shape of the data we're sending to Kafka so that we don't sort of create any more coupling within our application. And we can remove this coupling that might still remain in our application by using things like schemas and schema registries, which is another feature of Kafka. And schema registries can include things like Arpicuro. So a schema, in this case, defines the structure of the data in a record, and the schema registry is the place that we use to store these schemas. So there are various different open-sourced and vendor-provided schema registries for Apache Kafka, and they often provide additional features like validation and compatibility verification to make sure that producers and consumers can easily upgrade to new versions of that schema. So by sort of externalizing this data structure, we're able to make sure that we definitely have no coupling within our application code, and we can introduce even further resiliency when utilizing Kafka. So we've taken a very deep look at how we can introduce resiliency in the configuration of our application, in using tools and features like schemas and schema registries, and how there's inbuilt resiliency by Kafka's leader elections and brokers and topics and replicas. So let's take a look at the next behavior in the Reactive Manifesto, and that's elasticity. So how can we enable this scalability within Kafka? So Kafka is designed to work well at scale and to be scalable itself. As we said, this is all about placing events at the heart of our system in order for our applications to be able to scale and deal with data at scale. So in producing applications, we use partitions. And as we said, in topics, there is one or more partitions. Now, Kafka aims to be able to spread these partitions from a particular topic out across the different brokers. And this allows us to scale producers really easily, as we won't have load for one particular topic on one individual broker. We can also add additional brokers if we want to, and if that enables us to sort of spread the load out even more if we need to. So this is great in terms of Kafka itself, but we need to be considering scalability within our application. So how do we enable scalability when we're talking about the code within our application? And the area that we really see a big difference is in consumers. So in consumers, in consuming in Kafka, it's made sort of possible because of this whole stream history by using consumer groups. Because you have to handle this stream history and you have to know sort of what message you've read, whether another consumer has read a different message or record within Kafka, we have to utilize these consumer groups. So these consumer groups essentially allow us to group our consumers together so that we can know which consumers have read which messages and get that ordering guarantee. So we're able to know which groups are in which consumer groups because they essentially state a group ID in their configuration. So in this example here, we have two consumer groups. We have consumer group A and consumer group B. And in consumer group A, we have 3 consumers, and in consumer group B, we have 2 consumers. Each consumer here is representative of a different Java application. And as I said, they joined their consumer group by providing a group ID to Kafka when they started up, and that's in that configuration value. It's in a configuration file of Kafka. So once they've formed a group, Kafka will make sure that messages in the same consumer group read all of the messages within that topic. And this is where partitions come in again. So each consumer is essentially assigned one partition to read from. So in this case, you can see partition 0 is going to that first consumer, partition 1 to the second consumer, and partition 2 to the third consumer. But what happens when we don't have an equal number of partitions and consumers? So in consumer group B here, because we've only got 2 consumers, that means that essentially one consumer will be reading from one partition, but the second consumer will be reading from 2 partitions. So essentially, by enabling these consumer groups, we make sure that we haven't read duplicate messages. And from an ordering standpoint, Kafka provides this ordering guarantee per partition. So it provides this ordering guarantee for us. What happens if we want to add an additional consumer to a consumer group? Well, in consumer group A, if we add an additional consumer, because we don't have any additional partitions for it to read from, it essentially just sits there idle. Again, because of that stream history, that extra consumer can't read from the same partition as another consumer in the same consumer group, because that might end up with records being read twice or maybe missed. So it essentially just sits there idle. So when you're configuring your application, when you're setting up your application and setting up your Kafka clusters, you need to be considering how many partitions you're creating based on how many consumers you think might end up consuming from your application. But it is a delicate balance because when you can't add new partitions once your system's running, but the more partitions you have, the more load you're putting on the system when a leader election happens. And the other awkward part is if you add partitions once you've already started up the system, you lose that ordering guarantee. So do be careful. It's a delicate balance where you need to be considering, have I got enough partitions so that all of my consumers are actually, able to read from them? But equally, don't do too many, don't go overboard because you will add extra load onto your system when you're doing things like leader elections. So this is a really important configuration to be considering to enable that elastic behavior for us to be able to grow our consumers and to enable that scalability within our application. So I mentioned Backpressure as quite a useful pattern when we're implementing reactive systems, because again, it helps us to gracefully handle those potential sort of fluctuations in load. As I said, that's where that elasticity comes in as well. So Backpressure pattern consists of this feedback mechanism, and a Backpressure pattern that's often utilized is sort of TCP IP Backpressure. And this is normally achieved by having sort of separate send and receive buffers, and data is only sent between them when there's available space in the receive buffer. So you can see here on the bottom right, we have our receive window, and you can see our buffer, and that we'd only call enough data to fill that buffer. So rather than using a receive menu window and requesting data only when the downstream component has space, Kafka can be sort of introduced as a sort of infinite buffer. So where Kafka comes in is because we can just send events to Kafka and they get added to this topic, we can essentially, if a consumer goes down, Kafka can act as an almost infinite buffer for those messages coming in, because once our consumer comes back online, our consumer can start catching up with the messages it hasn't read yet and it needs to catch up with. However, Kafka doesn't have an infinite amount of space. So it isn't an infinite buffer, but it does help to act as a buffer between those aspects of your application, between those consumers and those producers. So this doesn't work for all use cases, unfortunately. There is, therefore, there's some level of backpressure is often required in systems that use Kafka. So essentially, that's where a lot of the sort of backpressure characteristics that we're going to mention later come into play in terms of the various different mechanisms that are used by the different reactive frameworks and toolkits. You can utilize the standard Java Kafka consumer client, so it does have this availability, this sort of ability to pause and resume consuming from Kafka, but it isn't an entirely sort of reactive form of backpressure. And this mechanism works well for consuming sort of simple use cases because it's modeled as a single loop. But where processing is fairly quick or perhaps complex, where we've got like multiple threads, for example, we are better off using some of the other sort of reactive frameworks and toolkits. So we've looked at how we can introduce elasticity, how we can introduce resiliency, and how we can utilize Kafka to really create a reactive application, essentially. So how do we go about writing this? How do we go about building reactive Kafka applications? So as I mentioned, there's a standard Java Kafka client, and that includes the standard Java Kafka producer and the standard Java Kafka consumer. Now, these enable some reactive behavior in, as I was saying, the pause and resume functionality, but they aren't designed to be really non-blocking and sort of reactive to the core. So that's where we like to sort of point people in the direction of reactive frameworks and toolkits. So we're going to focus on sort of 3 of the more common reactive frameworks or toolkits. This isn't an exhaustive list. These are just the ones we've worked with previously. If you're utilizing things like Spring Webflux, for example, you might be interested in Project Reactor, which is an additional framework we're not going to be touching on in this session, but is an additional sort of alternative to these technologies. So the ones we're going to be focusing on are sort of Akka or the Alpakka library within Akka, MicroProfile, and Vertx. And all of these have connectors to Kafka. So you can really utilize that reactive behavior for an application that utilizes Kafka. So the first one we're going to take a look at is Akka or the Alpakka library. So the Alpakka library essentially provides this Kafka connector API for us to be able to connect Kafka into Akka streams. And Akka streams is essentially part of the Akka framework or toolkit. So Akka is slightly different to many other reactive frameworks or sort of many other frameworks in general for helping you build applications, because it's based on something called the actor model. So it's not using microservices. So this actor model is essentially a paradigm or shift in thinking. So it's this conceptual model to deal with concurrent computation, and in it, the actor is the primitive unit of computation. So it's the thing that receives a message and does some kind of computation on it. Messages are sent asynchronously to each actor, and they store them in these mailboxes. Actors are able to communicate with each other by sending in these asynchronous messages, and that's where the asynchronicity really comes in. Actors also have this sort of hierarchy structure. So they have child actors and parent actors. So the parent actors can assign work or assign requests to child actors and monitor them as well. So it's a slightly different conceptual model. If you're already using the actor model, then Akka might be a great framework or toolkit to consider. If you're not, it is a little bit of a paradigmal shift. So just be cautious if you're looking at Akka as a framework to utilize for those reasons. So as I said, each of the different frameworks and toolkits sort of implement backpressure in a different way. So whilst we go through each of these frameworks, we're going to take a brief look at how they implement backpressure as well. So in the Alpakka Kafka connector, it handles all the pull requests to Kafka, enabling the application code to request new records using the standard Akka streams backpressure mechanism. So this mechanism is implemented according to the reactive stream specification, which was that specification I mentioned in the reactive programming section of this presentation. And it works on the basis that an application is essentially split into stages, where downstream stages advertise to their upstream stage when they're ready to receive more data. So kind of a similar concept to that TCP IP backpressure I mentioned earlier, where you sort of have that buffer space and you're able to send the amount of space that you have and request that from an upstream component. So this approach to backpressure, it will probably be familiar to developers who have previously used Akka streams within their application, but this is a learning curve to understand the syntax and to fully grasp the paradigm shift of adopting the actor model, like I said. So do just be cautious of that. But that's how the Alpakka Kafka connector enables backpressure by essentially advertising to the upstream stage when they're ready to receive more data, as you can see here. The next specification we're going to be looking at is Eclipse MicroProfile. So if you've not come across this specification before, it's a community-driven specification for enterprise Java microservices. And it's built and created and developed by a wide variety and a community of individuals, organizations, and vendors. And that includes developers that are sort of individual and they work for themselves, those who volunteer, but also developers from IBM, Red Hat, Pyara, and many, many other vendors all working together. So with MicroProfile, you get various different APIs and specifications. You can see here on the bottom, that sort of triangle shape, those are the specifications that come as standard with the MicroProfile stack. Now, the MicroProfile stack 3.3 is available at the moment, sort of fully production ready. 4.0 is in beta at the moment if you want to check that out. The one we're interested in, though, is a standalone project. So standalone projects are projects that the MicroProfile developer community still work on, but they aren't yet part of the main MicroProfile stack. And the one we're interested in here is the reactive messaging specification. So this reactive messaging specification builds upon the reactive stream specification and the reactive streams operator specification. And essentially what this enables us to do is to really enable sort of reactive behavior within our application by utilizing these annotations. So MicroProfile works by annotating an application's beans that contain methods. So we annotate those methods with either at incoming or at outgoing annotations. And these at incoming and outgoing annotations are matched up by something called channels. And a channel is essentially just an opaque string to match them up. Those channels can be internal or external. If it's an external channel, we call it a connector. So that way we can connect into systems like Kafka. Now the connectors, MicroProfile is just a specification, so it is implemented by various different vendors. We have our own implementation called Openlibity, and each implementation has its own connectors. So the connectors that will be available to you will depend on which implementation you're using in MicroProfile. You can see here an example of utilizing those annotations. We can see that we've connected up method A with method B by connecting that outgoing method annotation on method A with order channel to the incoming annotation on method B with that order channel. So you can see here how we can utilize those various different components. So how does backpressure work in MicroProfile? So it essentially works by using these annotations, and backpressure works in a really similar way to the Akka backpressure I just described. So the flow to downstream components is essentially controlled based on these components making requests for data upstream. So essentially what happens is we have the incoming annotation where we use our Kafka connector, we have outgoing annotation using a database connector, and that database connector might become unable to continue producing. So as a result, the Kafka connector can stop requesting new records. That's essentially how backpressure operates using MicroProfile in a reactive system. And as I said, there's very different implementations, including Openlibity, which is our IBM open source web application server. But there's also things like Quarkus and Small Mutiny. And these individual implementations of MicroProfile interpret this backpressure in different ways. So this is the backpressure for the Openlibity interpretation. Our last open source sort of specification or toolkit that we're going to be touching upon in this session is Vertx. So Vertx is a polyglot toolkit. So it doesn't just have to be used for Java. You can also utilize it for JavaScript, Scala, Kotlin, and many other languages. It's based on the reactor pattern, which is essentially an implementation technique of using really event-driven architecture. So it uses this single-threaded event loop, blocking on resource-emitting events, and dispatches them to corresponding handlers and callbacks. So that code is really single-threaded in Vertx. It includes this distributed event bus, which really allows us to place sort of that event-driven architecture behavior throughout our application, not just in our interaction between our app and Kafka. So Backpressure in Vertx, in terms of Vertx, it provides a separation for sort of polling from processing, and this gives developers the choice to either let Vertx handle the poll loop and this pause and resume functionality, or to handle the poll loop themselves. And this really helps with sort of backpressure within Vertx. So going into Vertx in a bit more detail, we actually used Vertx when we were sort of transitioning our Kafka application, our demo app, into a reactive Kafka demo app. So our demo app looks a bit like this. This is sort of a basic architecture diagram of what's going on within our application. If you want to check it out, it is on GitHub and it's all open sourced, including our UI. So you can check that out, and it's really useful for testing your Kafka to see if that's working. So in our application, we have this Vertx app, and that Vertx app produces events to Kafka and then consumes its own events back again, which isn't necessarily something you want to do in enterprise systems or maybe want to do in general, but it just helps us to show that Kafka is working and create this sort of very simplistic demo. And then we have a UI. We wanted a UI to be able to sort of see what was happening under the covers, so see those events being produced and see those events being consumed. And we send that information to the UI back and forth between the Vertx app and the UI via a WebSocket. So here is the application. As I said, it's all open source if you want to check it out. We more than welcome sort of improvements if you want to get involved and help us improve this application. Essentially, what we wanted to do with this application was we wanted to be able to start producing apps, sort of messages, then start consuming those messages back again. But then also we wanted to be able to stop producing and stop consuming and then restart again. And what this meant for our actual application is that when we built it as a non-reactive application, we had some issues in terms of pausing and resuming sort of that communication with Kafka. And we had some issues in terms of thread management when we were pausing and resuming. In terms of producing records, the benefits that we saw, so in the original application of the flow for producing records is fairly straightforward. So we have a start command that's sent to the backend on the WebSocket. That backend then starts the producer, which sends a new record every 2 seconds. Then we have a stop command, as you saw in that video, and that stop command is sent to the backend on the WebSocket, and the backend then stops the producer, and no new records are produced. But in the original application, using the standard producer client, the call to produce that record was a blocking call. But when we switched over to Vertx, that meant that Vertx producer was able to now use a future to get a future back from the send function. So you can see here, essentially this change, switching to Vertx and utilizing this future function, allowed the application to asynchronously produce these new records while waiting for the acknowledgement from Kafka of in-flight records. So this is a fairly small code change, but changing to a non-blocking when talking to external services like Kafka is a really important feature of reactive systems. So this made it easier to build the application to be resilient when these when these external services become unavailable. So you can see here how we were able to introduce more reactive behavior and sort of that focus on asynchronicity when we were producing records. But the biggest change we saw was when we were consuming and processing records. So in the original application, we were having to use this sort of for loop inside a while loop that resulted in the following flow. So we polled for records. That poll function returns a batch of records. We then iterated through each record in the batch. And for each record, we sent the record along the WebSocket to the front end. And then only after that iteration complete are we able to return to step 1 and poll again for new records, which meant that whilst we were processing the current batch of records, no new records could be fetched. So again, it was a fairly blocking, fairly synchronous process. It didn't feel very asynchronous. So you can see here, sort of focusing down on that loop. When we switched to the Vertx Kafka client, we were actually able to make this flow a lot simpler. So in the Vertx client, instead of using all of this sort of poll loop and having to wait and iterate, we basically use a handler function that can be called every time a new record arrives. So this really allowed us to have this asynchronous consuming and processing of records, which fit in much better with the reactive paradigm. So we made the flow a lot simpler, and now Vertx is able to handle the step of polling for new records instead of us in our application logic. So now our application code receives a new record and then sends that record along the WebSocket to the front end. So this not only allows the application to process on a per record basis, but it also leaves the developer free to focus on the actual processing of the records instead of the polling, instead of consuming them from Kafka. So it enabled us to sort of simplify our code and really enable that asynchronous per record basis of processing. We also wanted the ability to pause and resume, like I mentioned, both producing and consuming records from the front end. In the original application, where the default Java client was used, the while loop that caused the poll for the consumer needed to be exited and resumed based on commands from the front end. And because of this, the client is single-threaded. The loop had to be executed in a separate thread to the main flow of the application. Like I mentioned, this caused us all sort of thread headaches. Because we wanted to produce records on a timer, a similar while loop in a separate thread was required for the producer. So we had to deal with the headache of sort of writing this logic to control the thread lifecycle and synchronize this data across threads just to get control over the flow of records. Whereas when we introduced this sort of Vertx client and the Vertx application, we're able to use a combination of Vertx features and the Vertx Kafka client features to make the flow control much easier. So for the producer, we used a feature in Vertx that allows a handler to be called, like we mentioned. This handler can be called once, like we're doing, or multiple times, and it was easy for us to be able to pause and resume the timer when we wanted to start and stop requests arriving from the WebSocket. So you can see here how it really has helped us to really achieve asynchronous behavior within our application. We were also able to take advantage of additional Vertx features like the Vertx config to, again, instantiate more of those reactive behaviors that we want to see. So the Vertx config library essentially allowed us to provide a Kafka.properties file with all of our configuration loaded at runtime. So we essentially allowed us to switch between any different Kafka versions, so secure and non-secure Kafka endpoints. So we were able to move the application much more easily between Kafka installations if they're configured the same way. But it also enabled us to write it in a much more sort of cloud-native manner because we were able to externalize that configuration, similar to what's done in MicroProfile with the MicroProfile config feature. If you want to see those specifics and dive deeper into our application to see sort of what we were able to achieve by switching to that reactive-based application, Kafka application, we've written a whole blog about it here, and you can access that with the link at the bottom of the slide. So hopefully what I've shown you from sort of this demo, our application, and from the introduction to Reactive is that you can't just take a non-reactive application, add in a tool like Kafka, or just shove in an event-driven backbone and expect it to be magically reactive or magically non-blocking and asynchronous. Instead, you need to consider carefully the various different layers and levels in your applications and whether you're introducing reactive behaviors to each of them. But you also need to consider the Kafka configuration you're utilizing and whether it's the best it can be to make your application as reactive as possible. But you're not alone. Thankfully, the open source reactive community is on hand to help. There are lots of reactive toolkits and libraries available for you to utilize, all open source. And those reactive toolkits and frameworks can provide additional benefits as well for your application. So we're going to take a look at sort of how we can actually go about building a reactive application. And I'm going to show you just how easy it is to get started with some of those toolkits and frameworks when we're building Kafka applications in a reactive manner. So we produced these reactive labs. They are all based on the MicroProfile specification. So we've got I think there's about 7 in there. If you want to take a look at them, feel free. Or if you want to follow me along for this brief sort of interactive session, you can go to this link and we're going to be doing module number 1. So if you want to follow along and interactively do this alongside me, feel free to. This is all based on an online environment. So we're using IBM Cloud and Thea. So basically what it means is you don't have to have any prerequisites installed onto your own machine. So you can just essentially log in and the environment is created for you. So let's take a look at that now. So we're just going to restart. So I've gone to that link, and that link will take you to this sort of landing page. And this landing page shows you all the modules we have currently, and we are adding to this all the time. So do check back and there'll be additional modules here. The first module is the one we're going to be focusing on today. And this first module, I've lost my mouse, there we go. This first module is essentially just the basics of how to get started with MicroProfile Reactive messaging and sort of Kafka Java applications. The second module goes into testing in a little bit more detail, and for that we're using something called microshed testing, which is really all about running those tests in an environment, so in a container that's as close to production as possible. So that's a really great tool. If you want to take a look at that, check out Module 2. Module 3 is all about how to acknowledge those messages. So like I mentioned, that acknowledgement is really important for the resiliency within our applications. So check out Module 3 if you're interested in acknowledgements. Module 4 is all around integrating with RESTful services. And Module 5 is all about how to use a reactive JAX RS client to asynchronously invoke RESTful microservices over HTTP. As I said, the one we're focusing on today is Module 1. I've already gone into it, so we're just going to restart this lab. Now, we'll ask you to log in. So if you're logging in with me and trying this out, you will have to log in, but you can log in with most social logins that are available, or you can just log in with your email address. So let's get started. So the way this environment works is we have on the left-hand side, we've essentially got instructions that you have to follow and sort of key educational sort of points to point out whilst you're doing this. And then on the right-hand side, we have sort of essentially a basic IDE and a terminal. So we're going to jump straight in to sort of step number 1. So this application is based on 2 different microservices. We have an inventory microservice and a system microservice. So in fact, if I go back to step 1, we can see here, so it should let you know, so the system, here you go. So every 15 seconds, the system microservice calculates and publishes an event that contains its average system load. So that's the purpose of the system inventory microservice. And then the inventory microservice subscribes to that information so it can keep an updated list of all the systems and their current system loads. So essentially, those are the 2 microservices we're using, and they're connected together via Kafka. So we're going to be utilizing the Kafka connector from OpenLivity whilst we're using these MicroProfile reactive messaging concepts. So the first thing we need to do is git clone. So I'll just git clone that, and then cd into guide MicroProfile reactive messaging. We've created a start and a finish repository, and that's so that you can essentially start from a place where it's not, you just follow these instructions and you'll get to the finish guide essentially. But if you want to check out what the finish guide's meant to look like and compare it to what you're doing, then you can essentially check out the finish directory to compare and to sort of check out what it should look like at the end. So the first thing we need to do is create a system service class. So we're just going to do that now. And then we're going to go in and open that up. So we're going to open up guide MicroProfile, start. This one's for the system. So in system, SRC, main, Java, IO, OpenLivity, guides, system, and then there's our system service that we just created. So we're just going to copy in all this code that we've got here. So it's quite simple. We've already provided you the code that you need. But interestingly, the parts that I'm going to point out link to the presentation we've just taken a look at. So you can see here, because this is the system service, so this is the one that's producing every 15 seconds to Kafka, we're actually utilizing the outgoing annotation. So remember that those 2 annotations from MicroProfile were at incoming and at outgoing. So in this one, we're utilizing the at outgoing, and we're publishing to a topic on Kafka called system load. And you can see here we're using Flowable, we're doing it every 15 seconds, and we've got our average system load data. So we're actually using, so that flowable interval is actually essentially a method from RxJava. RxJava was, I mentioned it in the presentation, it's a reactive programming paradigm. So as well as using the MicroProfile specification for reactive messaging, we're also utilizing reactive programming within this application. The next thing we need to do is create an inventory microservice. So I'm just going to quickly do that now. Open that up again. So you can see here it's quite easy to navigate using our online environment to the different folders that I need to go into. So let's just navigate pretty much the same place, but this time in the inventory directory. And then we can see our inventory resource class that we've just created. I'm going to copy and paste this code in again. There's a little bit more in this one because we're consuming this time from Kafka. Save that. But you can see here, importantly, we've got that incoming annotation because we're consuming from Kafka. And we're consuming from the same topic that we were producing to in the system service class, and that's system load. So in order for this to work correctly, we essentially need to set up those config properties files. Similarly to the Vertx config, we're using MicroProfile config in this case to externalize our configuration. So I need to create that config file, and then I need to go in and open that up so I can add stuff to it. So I need to go into sort of start, because we're just in the start, and then we need to go into where we go, system, src, main, resources this time, meta-inf, and then microprofile config properties. So let's copy that in. So in here, you can see that we've actually got the outgoing, we're using the outgoing sort of annotation because this is the system properties. So remember that system microservice is producing to Kafka. And you can see here that the connector we're using is the Liberty Kafka connector because we're connecting using OpenLiberty to Kafka. As I said, each implementation has their own connectors, so this will change depending on which implementation of MicroProfile you're using. You can see here we've set our topic to be system load topic, and these serializers enable us to essentially serialize that topic into JSON configured using the value.serializer. So the next thing we need to do is create a similar file, a similar config file for the inventory microservice. So I'm going to go in and open that one up. So open it up in Guide MicroProfile Reactive Messaging, Start, Inventory, src, Main, Resources, meta-inf, oh, missed it, meta-inf, and then MicroProfile Config Properties. So in here, again, similar sort of config properties to what we had in the system config properties file. But in this one, we've got an additional one here. So we've still got the Kafka connector. We've still got the same topic that we're producing, consuming to in Kafka. We've still got the deserializer and the serializer. But this time we've got the group ID. Like I mentioned in the presentation, consuming in Kafka requires us to use consumer groups because of that stream history and in order for us to make sure that we're not consuming duplicate events. So this group ID allows us to essentially put this consumer in a particular consumer group. So that group ID is the additional config value you'll need to add for any consumer config properties files. So now we need to essentially create our server.xml configuration file so that we can add in things like the MicroProfile Reactive Messaging feature. So let's open that one up. Guide, start, and then system, src, main, liberty, config, server.xml. There we are. And let's add this in. So we copy and paste this in. We can see here that we've added in the MicroProfile Reactive Messaging feature. We're also utilizing MicroProfile config, like I mentioned when we made those configuration files earlier. So now that we created our server.xml file, we've done that for systems here. The inventory one's already been done for you. So if you are running through this with me, you don't have to create the inventory server.xml because we've done it for you because it's pretty much exactly the same. So now let's create the Maven configuration file. So we can do that using pom.xml. So here we go, and then open that up. Open. Now with this one, just be careful if you are following along with me on this, because there's kind of two in this file structure. Make sure it's the top one. Should be empty when you open it up. That should be a key sign if you've opened up the wrong one. So we'll copy and paste all of our configuration in. Oh, not the right one. Didn't copy it properly. There we go. So in here, you can see that we've actually got plugins for, there's the microshed testing that I was mentioning that we use in module 2. There's Rx Java that we utilize for that flowable method earlier. That's that reactive programming library that we're utilizing. We've got Apache Kafka in there as well. And here's the MicroProfile Reactive Messaging dependency that we've had to add. Because it's separate to the MicroProfile stack, you need to add that separately as a separate dependency. And here's the MicroProfile stack that utilizes things like MicroProfile config. But just remember that you do need to add the second dependency to enable reactive messaging using MicroProfile. So let's go ahead and essentially start running and installing this. This might take just a little bit of time depending on sort of whether you've run it before. If you've run it before, it should take less time, obviously. So we're going to start our Docker environment. So we've already provided you all the Docker files you need for it to get started with this application, if you are following along. Just wait for this to finish. Shouldn't take too much longer. A little bit more. Almost it. There we go, finished. So then Have I done my npm package? Just double check. Cool. So I'm going to skip this step. So this step just essentially makes sure that you're pulling in the latest version of our OpenLiberty sort of Docker image. If you want to check out which Docker images we have available, you can go and check those out on Docker Hub. We have lots of different versions available of varying sizes depending on your application. So we're just going to go ahead and sort of build this application. So first one we need to build is system, and then we're going to build the inventory microservice. Again, depending on whether you've run this before, it will take varying amounts of time. Perfect, that's done. And then we're going to essentially start our containers. So once those containers have started and we have our application up and running, what we can do is we can go to the inventory/systems URL to essentially access the inventory microservice. And what we should be seeing in the inventory microservice is that list of the values that it's consuming from Kafka. So what this curl command really enables us to do is check that our systems microservice has been able to successfully produce to Kafka, and that our inventory microservice has successfully been able to consume that data from Kafka, all using MicroProfile Reactive messaging, using those annotations, incoming and outgoing, and the channels connecting those, or the connector in this case to Kafka. So we just have to copy that curl command. Let's see if I've given it enough time already. Fantastic, yep. So you can see here that the data we get back shows me the host name and the system load data. Now, the interesting part is this is live, obviously, because we're getting your own system data. So actually, if you run that curl command again, you should see, yep, that system load changes over time depending on what you're doing with your machine, essentially. So you can see that is how easy it is to get started, sort of utilizing reactive messaging, utilizing MicroProfile Reactive messaging and RxJava, Kafka, and sort of open source tools like OpenLiberty. It took me about 10 minutes to get up and running with an application that's utilizing all of those functionality and is a reactive Kafka application. So if you are following along, you will need to tear down your environment. So I'm just going to quickly do that now. And then you can clean it up using our scripts here. So it's just stopping those containers for me. And then once it's done that, I'll do a cleanup. Yep. Oh, and you can see everything disappeared. So it's quite handy. And if you want to go back and do some of the other modules, feel free to afterwards. This is all running on IBM Cloud. It is our own environment. So if you have any feedback for us, feel free to send that my way. So going back to the presentation, so I've taken you through sort of a hands-on learning in terms of just showing you how easy it is to get started using these reactive frameworks, these reactive libraries and toolkits, and really making sure that Kafka is as configured to be as reactive as possible for our applications. If you want a recap of sort of what reactive systems are, why you'd want to use them and when to use them and how to, this really brief ebook can help you with that. It's a free ebook written by myself and my colleague, only about 30 pages long, so not too long to read. And you can access that using the link here on the left-hand side. Just a really great reference point for you to go back to or share with your colleagues if you want to dive into Reactive a bit more. If you're interested in sort of utilizing Kafka, but you want a supported version, we do offer IBM Event Streams, which is our supported version of Kafka with some value add-on capabilities. So, for example, the UI that you've seen in the videos that I've shown through this presentation, that in our application is the same UI that we use for our supported offering. So, if you enjoyed that UI, then we have the same UI experience for our supported version of Kafka. We also introduce things like that Schema registry that I mentioned earlier, which is a really fantastic tool for introducing extra resiliency within our applications. But we also introduce things like connectors, so connecting into MQ, for example, so that you can utilize both traditional MQ sort of queuing systems as well as Kafka within your application. So you can check out more information about that using the link at the bottom here. And as if I haven't given you enough links already, apologies for that, there are additional links that you can check out here. So if you want to take a look into sort of more depth into getting started with Reactive, then definitely check out our Intro to Reactive series or our article, Getting Started with Reactive. We've also got some great resources here for you getting started with Kafka. If you've not tried Kafka before, there's a fantastic quick start guide that you can check out here. It gets you up and running with Kafka in about 10 minutes. Do remember though that you don't just need Kafka, you also need Zookeeper. So you probably saw in that demo I just ran, we had some commands in there for Zookeeper as well. And that's because Zookeeper is still needed right now to store metadata for Kafka. In the future, that metadata will be stored in a topic in Kafka itself, but right now that's not released yet, and you do still need Zookeeper. So when you're running that quick start guide, make sure you run both. We've also got Stremzy on there. So Stremzy is an open source operator for Kafka, and it is produced by sort of an open source community if you're interested in running Kafka with Kubernetes. And then on the right-hand side, we've got some of those reactive Kafka libraries that I mentioned, including the Vertx library, the MicroProfile Reactive Messaging library, Project Reactor. So if you're interested in Spring or Spring Webflux, that utilizes Project Reactor, which is another reactive framework. And there's also Alpakka Kafka. And then the event streams link at the bottom. So thank you very much for listening. Hopefully I've shown you and taken you through sort of a deeper dive into how you can utilize Kafka and event streaming and reactive behaviors and characteristics to design applications and systems that are responsive to users and that are responsive to events that are placed at the heart of our system in this current event-driven world. With clicks, with sensors all over the place, IoT everywhere, and applications growing in the amount of data they have to handle. Hopefully these tips and tools will help you to sort of evolve your applications to be able to gracefully handle these fluctuating loads. So thanks very much. And I think we have some time for Q&A now. If I don't get round to your Q&A, or you have a go with the labs and you have something else you want to ask me later, then please do reach out on Twitter afterwards. Thanks very much for listening.
Thank you very much, Grace. So now I invite you to join our Q&A Zoom room to discuss all the details with our participants. And thank you very much.